Hello. This is sort of a crash course in heat transfer, so we'll talk about a few issues that you need to understand, and we'll relate these to civil engineering. And we have already talked about the three modes of heat transfer: conduction, convection, and radiation. And radiation should not be confused with the radiation from a microwave oven. It's totally different, okay? It's electromagnetic radiation emitted by an object when it exchanges heat, which is different. So we have conduction, which is through solids or stationary fluids, and convection uses the movement. And remember, this is the key here. The movement of solids is the key. If you have air and it's moving, like in a fan, then it's convection. So otherwise it's conduction. So there's three different units that are used to talk about heat transfer. We have the thermal energy, Q. This is what we have talked about and we have calculated. And also we have talked about heat transfer rate, which is the rate would be the energy divided by time, which is watts, which we also have talked about it. But then there's the flux. That's the new term. And the heat flux would be the heat flux rate. Here we have the watts divided by an area. So let's say that you have a specific area and then you have heat that is being emitted by another source. So here you have Q, and then let's say you have it per time, so you have your heat transfer rate, and then here would be your area, so that heat transfer rate per area is the heat flux. And flux is a very important term, not just in heat transfer, but in mass transfer. If you ever are involved in any research project that has mass transfer. So these are several examples, and we already have seen this in class. You might want to take a minute and read over each one of these. So if you want to pause the video and read it, feel free to do that. Otherwise, I will move ahead. So conduction is the first one, and we have defined conduction as well. When you touch an object that's hot, there's conduction. So it's through solids, and it can be solids or fluids, but not in motion. And we had mentioned how it's due to molecular collisions. When molecules vibrate, then heat is released and transferred. So also by particle collision, solids, especially metals that have free electrons, they're not bound and freely move, and so they collide and become warm. So this is a very important mechanism, and so what you'll see is that materials that are good conductors, generally speaking, are good conductors of heat, are good conductors of electricity. So we're going to talk about steady state conduction in this class. We're not going to talk about unsteady or transient state. Generally, what happens is that the heat that is being transferred, if you have a pan that's cooking, you turn it up first, and the source of heat is constant, but the heat is being transferred. That is being transferred is changing with time, so that would be transient state. So whenever you have steady state, there is no change in heat transfer with time. And this is what we will focus on, steady state. So the rate of conduction through the object or heat transfer rate, remember rate, we have, let's first talk about conduction, and this slide focus on conduction. You have the handouts that have convection and radiation, but the principles are the same. So what you have is that this rate of conduction, which is Q, equals minus K, and K is the conductivity of the material, and it's the property of the material. You find it from tables for different metals or ceramic materials, aluminum, lead, stainless steel. A is the cross-sectional area through which the heat is conducting, and delta T is the temperature difference between the two surfaces separated by a distance delta X. So if I have this object, whatever it is, and I'm putting it vertical, it could be horizontal, and so we have a difference in temperature. So here, let's say that I have T1 here and T2, so this is the difference in temperature. So this has a thickness of delta X, is like a distance or a thickness. Sorry about the handwriting there. And so we have the difference in temperature, the difference in distance, and the conductivity of the material, and then the area through which this is occurring. So if this was a 3D material, then you also have this area through which heat is conducting through. Okay? So that's very important. If you're holding a hand and a cup, well, that area would be the area of contact between the hand and the cup. That is the heat transfer due to conduction. So you have to look at the area that it's serving as transfer for the heat from one side to the other. We will do one-dimensional conduction, and as I mentioned to you, it's important to relate this to civil engineering. So in civil engineering applications, generally, we use the thermal circuit model. So what we do is that we analyze heat conduction on any material the same way that we analyze electricity transmission. So we will define a thermal resistance instead of just a resistance in terms of electricity. So the thermal resistance, and this is for conduction, okay, would be L, which is the thickness layer, and this L is what we had called earlier delta X. K is the thermal conductivity, and A is the cross-sectional area. So all of this is the same concept, just they call it differently for some reason. So this is the resistance, thermal resistance due to conduction. Okay? Whenever we have conduction and convection, then we also have a resistance, and it's 1 over HA. So let me just review real quick the expression for conductivity, thermal conductivity due to conduction, and that was minus Ka delta T over delta X. And then for convection, we have Q equals minus H A, and then T at the surface minus T, we call this. And let me give you an example of this. So whenever we're talking convection, let's say that I have a fan here, okay? So, and I have an object here. So this would be the temperature at the surface. And this would be away from the surface, like T infinity. So it would be that distance away from the surface. And if I'm referring to this wall for convection, then I this would be the area, unless I'm talking the whole area, so you have to be very clear of what is the area that we're talking about. And then H, of course, is very similar to that K. In the case of the K, that meant the resistance, the coefficient due to conduction, but in this case of convection is H, not K, okay? So K is the conduction coefficient. Oops. And H is the convection resistance, or coefficient, sorry, convection coefficient. Okay? So I hope that clarifies. So then we have the resistance, thermal resistance due to conduction, and thermal resistance due to convection. So we do have resistors in series and in parallel, the same way that we did for electricity. So if I have a resistance due to conduction, then I express it like that, and then I have a resistance due to convection. And let's say that I have another layer due to convection. And you can go on and on. I can have 3 layers, 2 layers, 4 layers, it doesn't matter. If they're in series, then the total resistance is added, just like you did in electricity. Now, if you had it in parallel, like this, then you have, if you have here conduction or convection, then you have to add the inverse of the resistance. So like 1 over R1, 1 over R2, and so on and so forth. So we will deal with it in the same way that we had before. So then, what do we do with that information? Well, the total heat conduction then would be that total resistance that you added, okay? And then you have your initial and final temperatures, okay? And that is how you calculate. Now remember, here it says initial and final, but it refers to the two ends. So if I have something like this, a surface here, another surface there, another surface here, this would be the initial and this would be the final. So it would be like T1 and T2 on the extremes or the sides of the elements that you're analyzing. So this is an example problem. You do have these the slides in Blackboard. They have been uploaded, so I encourage you to look at these. And what you see here is that you have conductivities of different layers, and then you have some convection coefficients. And so in this case, you also have conduction coefficients. Remember, the K is for conduction and the H is for convection. So what happens is that you define the resistance for each one of those. And here you have, in layer 1, it says that you have conduction, K1 and K3, okay? And you have to determine the total resistance and, of course, the heat flow. So if you look at these layers, what you would have is, okay, you have 3 in series, but then the 4th one is in parallel. So here I have 1, 2, 3, and 4. So what you would do is you add up the resistances of 1, 2, and 3, and then you'll get a total resistance 1, 2, 3, and then now you have 4. So now you have a summation of 1 over R23 plus 1 over the resistance in 4. Okay, so that's, I'm just giving you the overview. So what we have here is K1 and K3. One, you have a conductivity, they give you a K, right? And for K3, they have a K. And then you have K4, okay, and we have a convection coefficient on either side of the composite. So this would be like a composite wall, for example, that has different materials and different modes. It could be a window with different materials and different fillings. So, of course, I already told you the generic solution. I forgot to include the last one because it talks about the convection coefficient. So you have, and also another convection here. So this is what we have. So you have to present it as resistances so that you know that you have to start simplifying, and you start by simplifying the resistances in series and then combine them with those in parallel, like here. And then you have this one in parallel, so you get one resistance here, and now you have it in series. So that would be your first step, to calculate the thermal resistances. And I'm going to go real fast here, so if you want to stop, pause it, and look at it, or print your slides and look at this, would be perfect. So here are the calculations for each one of those. And so the step 3, you find the series and parallel resistances, and you have to simplify all of them, and you will find the total resistance. And so the heat transfer through the composite would be Q, and then you have T1 minus T infinite over R total, so you have 173.9 watts. Now remember, that's joules per time, okay? So if you have joules per time and you have a stove and you know how much joules you're adding, then you can predict how long it'll take to cook. Hint, hint, for those cases where I would ask you to determine the time. So basically that's it. That's a simplification of everything. These are lecture notes courtesy of Dr. Ioannis Nouelis. He's the director of the Boston Science Museum. And you have a homework to be turned in at the final exam, problem 1717 and 1728E. Now, how can we relate this to civil engineering materials? Well, we talk about the R value, which is what we calculated. So this is kind of the designation that's used in the American unit system. Also, you can see the U factor, or the U value, which is the inverse of R. So if you have an R value of 2 that has a U value of 1 over 2 or 0.5, so it's kind of opposite. So higher R value is higher insulating value, whereas lower U value indicates higher insulating value. So this would be R very high. And you can find this link that gives you the insulating values and the recommended values for different areas in the U.S. where it's recommended. You need a better insulating value if you're in Alaska or in Canada, of course, because of the extreme temperature differences. So please go to those links and review those terms. And then for windows, you need to choose wisely. Windows are thermal holes, meaning that a lot of heat is lost with the windows. An average home loses 30% of its heat or air conditioner energy through its windows. So that is important. You can go to those links. I hope this has been helpful. Have a great day. Thank you very much.